Hello everyone, welcome to the second in this short series of 3 lectures introducing high performance computing. In the first lecture we talked about high performance computing and different architectures and how the hardware is built up. In this lecture I want to focus more on the software. How do people actually exploit these parallel architectures? What tools and methods are there to help people use them and write efficient programs? So this is the introduction to parallel computing concepts. As before, as a standard slide on how you can reuse this material if you want to. What we're going to look at is why use parallel programming. So this is be a quick rehash of why use HPC in some senses. Look at some basic concepts that you need to understand to be able to understand parallel program methods, processes, and threads. And then I'll talk a bit about 3 different parallel programming method models in this lecture: message passing programming, shared memory programming, and hybrid models. That's not to say these are the only models out there, but they're the ones in most common use. So they're probably the most useful to understand in the first instance. So why do people do parallel programming? Because it is much more difficult than sequential programming. So the reasons are the same for the reasons of why build parallel machines. We've reached a limitation in terms of producing a single piece of hardware, a serial processor that can do the work required due to physical limitations and the development of new process technology and some of the fundamental laws of physics. So the way to try and improve performance without just making a faster and faster processor core is to use more of them and split the work up between multiple cores, and this is hence the parallel programming. But it's not very, like I say, it's not simple. It's not a silver bullet. There are many additional considerations you have to take into account in terms of algorithms and things like that, and you have to really think carefully about what you're doing to be able to take advantage of parallel machines, because quite quickly you can get into the space where you've expended a lot of effort parallelizing your code and you don't get any return for it because of a poor choice of algorithm at the start. The key to everything is performance and high performance computing. So what we're trying to do is solve problems faster or solve bigger problems than you could on a single machine. And to exploit parallel computers, obviously we need to be able to split the problem up, the program up, between different actual physical processors. So ideally, given P processors, we want to run P times faster. Okay? So we split it up perfectly, should go faster. The problem is that not all parts of the program can be successfully split up. For example, it's very difficult to split up I/O and disk access. And splitting up the program also may introduce additional overheads into our programs, such as communication and other things on this line, along these lines. So all of these things have to be borne in mind with programming. If you're not a programmer, why would you want to understand how parallel programs are produced? Why are you interested in this lecture? Well, appreciating the constraints and the way in which parallel programs work allows you to better understand how you can use parallel programs to solve your research problems. So say you're using GROMACS, it allows you to understand why GROMACS performs the way it does and how you might split up your problem, or how you could change the way you're posing your problem to make something like GROMACS run better, and help you understand why some things work well on parallel machines and others don't. Okay, so having an understanding of these concepts, a very high level understanding as we go through in this lecture, will help you in your own research and understanding the research of other people. So there are a couple of concepts we need to understand to be able to explain why different parallel programming models work in a different way that they do. And these are to do with the operating system and how an operating system works, and in particular how it schedules different tasks to the cores that are available. And it does this in 2 ways through 2 concepts. One is processes and the other one is threads. First of all, the operating system, what is it? There are a number of different operating systems out there, for example, Mac OS or Windows or Linux, and even other ones, the OSs that are used for mobile phones, such as Android and OS X. And what the operating system does is it orchestrates access to hardware by the applications that are running on your computer. So it orchestrates access to cores. Which cores are your application running on? How is the memory allocated and deallocated and divided between different applications? How is the file system access? How do you go to disk? Who has the rights to do what? Who has the authority to access which resources? And how do we deal with oversubscription? For example, more applications than cores available. So many people run on their laptop, I don't know, 5, 10 programs, and generally they'll have a quad-core quad-core processor in there. How does the OS deal with this? How does it make sure that the right application has access to the core at the right time? And these running applications are controlled through the concepts of processes and threads. We'll deal with processes first because they're what people most commonly come across. So each application is a separate process in the operating system. So each application I'm running on my laptop, be it PowerPoint, a web browser, an email client, each of these is a separate process. Each process has its own memory space, which is not accessible by running processes. This is how we stop security breaches. So somebody gets access through some malware on your web browser, they can't use it to corrupt, hopefully, your email client or another application running on the system. And each process is scheduled to run by the operating system. It can be tied to a particular core or migrated between cores. In practice, the core migration doesn't happen very often. And this is no different to a HPC machine, because if you remember from the last lecture, each node of an HPC machine is essentially like a separate computer, individual computer running its own version of the operating system. So those operating systems on each of the nodes are independent and schedule processes, as my laptop does here. And if a process stops for some reason, say it's waiting for a file from disk or something like that, quite often the operating system will notice this and swap in another process that's waiting for access to a core to take advantage of it. And this swapping, this interrupt process, happens on quite a small division of time. And this is what's called process scheduling. So the operating system has responsibility for interrupting the process and granting the core to another process. Which process is granted access and is determined by the scheduling policy. So in terms of maybe some types of application have a higher priority than others. Maybe some types of application cannot be stopped to make way. They're so critical that you can't pause them while another application goes in. This interrupt happens regularly, usually every 0.01 seconds or something like that. And the process that you're selecting to put onto a core should really have work to do, otherwise there's no point pushing it in. So some hardware can also support scheduling of multiple processes as if there's more cores available. This is called symmetric multithreading. So what it'll actually look like on your machine is, instead of the physical 4 cores you have on a quad core, it might look like you've got 8 cores instead. So the operating system doesn't know anything about this. All this sees is what the hardware presents, which is 8 cores, and it uses them as it sees fit. The hardware sorts out some sort of scheduling at a lower level. Process scheduling actually can be a hindrance to performance. So particularly in high performance computing, where on a compute node you know you're the only application running, you don't want the operating system to keep going and looking and seeing if there's something that gets swapped back in, because every time it does that, it costs you some performance. So there can be a bit of tuning of the operating system that goes on high performance computing systems, particularly on the compute nodes, to try and stop this interrupt process happening. The other concept you need to understand is threads. So for most applications, each process is a single thread. Right? It's just you've got the process. We had that picture before. The process is all running in parallel. But with the advent of multi-core sockets, then it's becoming more common for each process to contain multiple threads. Okay, so the difference between processes and threads is that threads all the threads in a process have access to the same memory. Okay, so remember, separate processes could not access each other's memory. So then they can operate in parallel on the same data to speed up applications. And you can have threads operating asynchronously, so they can swap in and out and do different things. And so, for example, on my laptop, one thread, if I'm running PowerPoint, might be displaying the slides on the screen, while the other thread might be listening for mouse application or touchpad interactions and deal with moving the pointer around. Okay, so they're both running within the same application, so they have access to the same memory, but they're both doing different tasks. And in parallel computing worlds, one you often see would be, for example, a vector dot product. Essentially, you want to perform the same operation on multiple numbers in a vector, and you could split up that operation between two threads, so hopefully then it would go twice as fast. Okay, so that's and the operating system is also aware of threads and can schedule them in the same way as it can processes. But the switching between threads is usually a bit quicker than switching between processes, and usually you only schedule one thread per core, but that doesn't have to be true. So armed with this concept of a process which has its own memory, which other people can't access, and threads which share memory, we can now construct some parallel programming models. The first one I'm going to talk about is the one that's most widely used, probably in 80% of programs that run on HPC machines, and this is a message passing programming model. So the message passing programming model is process based. So processes run simultaneously, fine, on multiple cores on our HPC machine, and they communicate by exchanging messages. And they have to do this, remember, because they can't access each other's memory directly. So the messages can be two-sided, both the sender and receiver involved in the process. So that's almost like, I guess, a parcel delivery in some senses. So I might send a parcel to you and you have to sign for it at the other end. That's two-sided because both I'm involved, I've had to physically send the parcel, and you're involved, you've had to physically say, I've received this parcel by signing for it. Or they can be one-sided, which is maybe more like letter delivery, standard letter delivery, in that I can send you a letter and it gets put in your postbox. You don't have to do anything at the other end, and unless you want to open the letter and look at it and reply to me. But that's a single-sided thing. Only I'm doing any really active action there. And it's used for both data and task parallelism. What do I mean by data and task parallelism? So by data parallelism, I mean that I have a certain amount of data which I want to operate on in parallel. So a standard example of this is the one I used a moment ago of a dot product. I've got a huge array of numbers and I want to multiply them all by a constant. So I can split up that task and send different parts of the array to different cores or different processes in this message passing model to all do it, and hopefully speed up the process because they're all doing it in parallel. That's data parallelism. I'm acting on the data in parallel. Task parallelism is where each process is doing something slightly different. So an example of this is when you're doing molecular dynamics simulation. Often you want to do two things. You have the short range force interactions, for example, a Leonard-Jones potential, and you have the long range forces, the electrostatic interactions. It's often treated through something like an A-world sum. And I could use some of my processes to do the pairwise force interaction and some of my processes to do the electrostatic calculation. In this case, this is task parallelism because different processes are doing different tasks. In fact, most message passing programs that are out there employ a mixture of data and task parallelism. So often they'll have bits where they're operating on different bits of a large data structure in parallel, and at other times the processes will be doing different parallel tasks. So here's a picture that I'm supposed to illustrate this. Is that each process doesn't have access to each other process's memory. Fine. So the communication has to be explicit. So I say, I'm process 0, I'm going to send a message to process 1, and process 1 will, in two-sided communication, will say, fine, I've got that message now. Okay. So here it is the responsibility of the programmer, the person writing the program, to specify how the processes communicate with each other. And there are libraries that can abstract it for particular operations and things like that, but essentially it's an explicit parallelism. Advantages and disadvantages of this method. One is that it's very, very flexible. If you can imagine a parallel algorithm, you can implement it using message passing programming. And the scaling is really not limited so much by the programming model, but your choice of algorithm. Okay, so if you have an algorithm that scales, then you can make it scale. It's very portable. The MPI library, which we'll talk about on the next slide, which is the common incarnation of message pass program, is provided on any HPC platform you come to. The disadvantages are that the parallel routines become part of the program due to the explicit nature of the communications, right? So you'll see in your program calls, and this can mess up the structure of your code a bit and make it difficult to debug and understand what's actually going on. And it can be a very large task to retrofit it into existing serial code. It may not give the optimum performance on a shared memory machine because you've got this extra software layer of passing messages when you maybe don't necessarily need to do that on a shared memory machine. And it can be difficult to scale in some senses to very large number of processors due to overheads, although there's active work going on in this space to reduce this problem. And depending on what sort of algorithms you use, you can avoid this problem as well. And the most common incarnation of, or essentially the standard incarnation of message passing program is in the message passing interface library, MPI library. And this is a portable library for writing parallel programs using the message passing model, and it's available on every HPC platform you come to. It's based on a number of processes running independently in parallel, which we've talked about already, and you usually get some sort of command that launches these that coordinates the launch of these multiple processes simultaneously, so you don't have to do that by hand. So you'll often see things like MPI exec, and you specify the number of processes, and it gets launched. They get launched in the right place automatically. And there are a number of different implementations of MPI, but they should all support this MPI2 standard. And there'll be variations, but all of them should work. So for examples include things like MPitch2 or OpenMPI. And this model is used, and the MPI library is used for the vast majority of codes that run on HPC systems. So shared memory programming is a little bit different. It's usually based on threads rather than processes. And if you remember, threads exist within a single application, can access, and all threads can access the same memory. Some hardware software allows processes to program as if they shared memory, and we saw some of them. We talked a bit about that in the first lecture in terms of shared memory architectures where you can use a software layer to imitate shared memory. It's also known as symmetric multiprocessing, SMP, though that term's now a little old-fashioned, you don't meet it so often. It's most often used for data parallelism. This is where you want to operate the same set of instructions, the same mathematical operation usually, on a separate bit of the data. And is generally more difficult to use for task parallelism where each thread is doing something slightly different. So a picture of what it looks like is given here. This is for some sort of operation on a vector with 8 elements. So our process comes down here, it splits into 2 threads. Each thread operates on one half of the data and then they join again and carry on. This is called a fork join model, and you'll often see fork and join. The threads sort of communicate implicitly by having access to the same memory space. Okay, so here the communication is very implicit. There's no explicit communications between the parallel tasks as there was for the message passing example. Any thread can alter any bit of data, and that actually introduces complications in programming because you have to be very sure of what the state of memory is before you go altering any bits of data in it. So the advantages are that it's really conceptually very simple. Most people understand shared memory programming, at least at a high level, without too much difficulty. Usually only need very minor modifications to existing code to take exploiter. So usually if you have a loop in your code that does some sort of vector operation, you'll just put some extra extra statements above and below the loop, and then you can introduce this shared memory programming into your program very easily. And it's very portable. Almost all compilers now support the OpenMP standard, which I'll talk about on the next slide, which is the standard incarnation of shared memory programming. The disadvantage is there's a lack of flexibility in the terms of algorithm that can be encoded, because it can be difficult to implement task-based parallelism. It doesn't scale very well generally because, well, two things: because of the hardware, the type of hardware you have access to, and shared memory doesn't generally have very many processors, so it's very hard to make it scale well. And also because it's data parallelism. You can imagine that if I want to use 1,000 processors, I'm going to need a lot of elements in my array to be able to give each of those 1,000 processors enough work to make it worthwhile. That's because it requires a large amount of inherent data parallelism. And it can be surprisingly difficult to get good performance, and this is because the memory subsystem and the memory structure of modern computers is quite complex, with different levels of cache, things like that, and you have to start worrying about these things. And then you have to start worrying about the data integrity and who's modifying data when as well. So it can be surprisingly more difficult than people think to get good performance. So, and it can be difficult to find the right level to introduce this shared memory parallelism. If you include it at too low a level, you're starting and stopping threads very often, and you get a lot of overhead. If you do it at a too high level, you don't gain that much performance from it, and you may as well have used message passing or another concept better suited to task parallelism and things like this. But the standard model for shared memory programming is OpenMP, and OpenMP is supported by all compilers on all HPC platforms. It's not really a library interface like MPI, so you don't put explicit calls to OpenMP routines in your program. You put directives into your program source, and the OpenMP is added automatically by the compiler. And the parallelism is less explicit than MPI than the message passing model. So most codes use MPI for distributed memory architectures anyway, and you see some OpenMP codes used on shared memory architectures. A model that's becoming more common is a hybrid of the two, because as you saw in lecture 1, most HPC machines are made up from shared memory nodes connected together in some manner. There are these different hierarchies of parallelism. So there's a shared memory level, which might think might be best suited to using something like OpenMP, and then there's the distributed level, the level above it, which might be more suited to a message passing interface in MPI. So this MPI OpenMP combination often maps more closely to the hardware layout and you can use it to expose different levels of parallelism within the code. Okay, so you can do your task-based parallelism maybe with MPI, and then do the data parallelism within a node using OpenMP, which is generally quite a nice thing. It generally doesn't lead to raw speed up, but it does allow the code to use memory more efficiently, and this is becoming very important as HPC architectures develop. You'll see in lecture 3 where HPC is going, in that there's going to be less and less memory generally available per core, so your programs have to be more and more memory efficient, and it allows the code to exploit more cores for your problem, so improving the scaling of the code. And the complexity of the implementation depends on the code, right? But lots of codes out there allow people to use hybrid MPI OpenMP seamlessly, even if you're not a programmer. So for example, if you use GROMACS, it's built into the code. If you use CP2K, it's built into the code, and it's quite easy for a user just to exploit this complex programming model if they're using the code. So in summary, power computing, the idea behind power computing is it opens opportunities for new research. Either it speeds up time to solution, so you can do more of these calculations, or it opens up possibilities that weren't available before. You can treat larger systems, you can use better statistics, you can use different algorithms. MPI and OpenMP dominate parallel programming in HPC codes. MPI for message passing programming, distributed memory, and OpenMP for shared memory programming. And MPI is more general purpose, and it requires explicit specification of parallelism, but the scaling is usually dependent on your algorithm choice rather than the inherent limits of MPI itself. OpenMP can be simpler to implement, but the performance is generally limited by the size of the shared memory part of the hardware. And experience has shown that scaling to high core counts using pure OpenMP is very difficult. Okay, so that's the end of lecture 2 in this series. The third lecture on the future of HPC is the next one to listen to. And as before, if you have any questions or you're interested in parallel programming, please have a look at the EPCC website, and we'd be happy to be in touch with you about your work and whether you think parallel programming can work for you.